Welcome to Lecture 5.2, Public Key Cryptography and RSA. The RSA cryptosystem was developed at MIT in the late 1970s by Ron Rivest, Eddie Shamir, and Leonard Edelman. That said, as often happens with cryptography, nearly 20 years later, after certain documents were declassified by the British government, it was discovered that a mathematician actually developed an equivalent system about 5 years before this. RSA allows two people or two entities to exchange messages in plain sight. To illustrate what I mean by this, suppose that I want to send you a secret message, for example, your midterm exam score. For privacy reasons, I cannot just email it to you in plain text, because what if somebody snoops? Instead, you create a publicly available encryption function, E of x, and we'll learn how to do this. So you send me that function, and then I plug your score into that function, compute it, and I email that to you. Because you created this function, you have secret information that allows you to easily compute the inverse, which is just the decryption function, and we'll call that D. However, for everybody else, without this secret information, decryption is basically impossible. RSA is an example of a public key crypto system, and these are widely used today. You use them every day, whether you know it or not. Well, you don't use them, but they're used behind the scenes. Anytime you enter your password into a website, you're not actually sending them your password. Your password doesn't sit on their server in plain text because an IT person could uncover it or a hacker could get it. What you're doing is you're sending them an encrypted version of your password. So a hacker with that information wouldn't have anything to do with it. Now, if a hacker could also get into your personal computer and find out your secret key, by secret key I mean the secret information, then, yeah, they could figure out your password. But one's a server, and one is just a random PC in your house. All of these public key crypto systems are characterized by some encryption function, E, that goes from a set to another set, think like maybe an integer to an integer, for example, that is easy to compute. So anybody can compute it, but almost impossible to invert unless you have the so-called secret key. Unlike the methods in the previous lecture, which were symmetric crypto systems, both parties had the same information, public key systems are asymmetric. One party will have a private key, and the other one just has the public key. Let's go through an example to see how RSA works. So remember, I'm trying to send a message, like your midterm score, to you, just a single number. Now, as the intended recipient of the encrypted message or messages, you need to take the following steps. First, you need to choose two large primes. Don't tell me what they are. In practice, these have to be about 200 digits in length. To make things easy, let's just suppose you pick small primes. Suppose you pick 17 and 19. Remember, I don't know these. You keep this secret. Next, you are going to multiply those two prime numbers together, and we'll call that number n. So in this example, 17 times 19 is 323. This is not a secret. You can disclose this publicly. Now, obviously, if you tell me that your n is 323, I can, with the help of a computer or by hand, factor that as 17 times 19. However, in practice, if your primes are several hundred digits in length, and you multiply them together and get a number that's, 3, 4, 500 digits in length, it's impossible for me to factor that, even with the aid of a supercomputer. It would take more time than like the It would take probably hundreds or thousands or even more years. You basically need to know what one of the primes is to factor it. For the third step, you will compute a special integer, let's call it a, which is just p minus 1 times q minus 1, or 16 times 18, which is 288 in this example. Now this has a special name and special symbol from number theory. It's called Euler's totient. Euler's totient. I don't know where that name comes from or what totient means outside of this context. And it's written phi of n. And phi of n is defined as the number of integers less than n that are relatively prime to n. So formally that is the size of the following set. The size of set of all k, where k is between 1 and n, and the GCD of n and k equals 1. Okay, so in the special case, when n equals p times q, which is what we have, almost everything is relatively prime to n. The only things that are not are the multiples of p, and there are q of those, and the multiples of q, and there are p of those. So let's see. So we have phi of n, that there are n possible candidates. There are n numbers in this range that could be relatively prime, but we have to subtract off the p multiples of q that we know are not relatively prime. We have to subtract off the q multiples of p that are not relatively prime, and then we've actually double counted because we've counted n twice. So by inclusion-exclusion, we have to add back 1. And if you look at this, you notice that that actually is p minus 1 times q minus 1. So in general, it's hard to compute phi of n for a given integer, but it's easy in a few cases. For any prime, it's just p minus 1. Every number other than the prime is relatively prime to it. And for a product of two primes, it's p minus 1 times q minus 1. So this number you can compute easily because you know p and you know q, but nobody else knows how to compute that. That said, this is going to be part of your private key. This is something that you will use to compute your private key. So don't share this with anybody else. Certainly don't share it with me. I'm the one who's sending you the message. In your fourth step, you will use this secret information, 288, that nobody else knows, that you got from these primes that nobody knows, to compute the other part of your public key. Namely, you will pick an integer, let's call it e, that is less than phi of n, in this case 288, that's relatively prime to it. That's all you need to do. So in this case, let's just pick 95. I'm going to tell you that that works. Don't worry about how to actually compute it now. At this point, I just want you to treat it like a black box, something that isn't that hard to do, and I'll show you how to do it. It's especially not hard if your numbers are just several digits long. You can easily just guess and check. But it's more difficult if your numbers are several hundred digits long. So we'll learn how to do this in a bit. At this point, your public key is the ordered pair consisting of n and e. That's 323 and 95. You can share this with the world. Put it on your website, email it to anyone you want to, and anyone who has it has the ability to take a message of their own, encrypt it, and send it to you so that only you can read it. Only you know how to decrypt it. Anyone else who sees that wouldn't know what to do with it. And here's how they do that. Your public key defines your public encryption function, which is just x to the e mod n. In this case, x to the 95 mod 323. So I will take your midterm score, which is some number. Maybe it's like 86, say. And I will raise that number to the 95th power. And then I will reduce it mod 323. That will give me a number between 0 and 322, inclusive. I will send you that number. And so if an onlooker gets that number, maybe the number says 176, that doesn't mean anything to them. Even if they know 323.95, that in order to figure out what number that came from, they have to know A. They have to know 288, phi of n. And they don't know that unless they actually know the primes themselves, which they don't. So I send you your encrypted midterm score, and all you need to do now is decrypt it. So you need a decryption function, and you will define that from your private key, which we will call D. And D is computed using the knowledge of this special number 288, phi of n, up here. Specifically, D is the multiplicative inverse, remember that from the previous lecture, of E mod A. Remember what multiplicative inverse means? That means it's the thing that you multiply by E to get 1 mod A. So specifically, it is D is the solution to the equation E times X is equivalent to 1 mod A. Whatever works for X, that's your D. Once you have your D, you have your decryption function. And it's very simple. You take the message and raise it to the dth power modulo n. Now, the message that you are decrypting, remember, is just my message raised to the eth power, because that's what y is. So notice y to the d is x to the e to the d, which by the laws of exponents is x to the e times d. And remember, e times d is equivalent to 1 mod n. So x to the ed is just x to the first. And x is the original message. So you've done it. In this particular example, your D ends up being 191. So your decryption function that only you know is y to the 191. So in other words, you publish to the world this function. You said, if anyone wants to send me a message, take that message, raise it to the 95th power, and reduce it mod 323. And then what you'll do when you receive a message is you'll take the message you got, raise it to the 191th power, and reduce it mod 323, and you will recover the original message, and no one else can do that. So first of all, here I'm assuming messages are numbers. As we've seen in the previous lecture, we can break up a longer message into a string of numbers and handle it that way. But we'll talk about some of the details of that later. For now, it suffices just to see how to send numbers. Let's summarize the example that we just did. So I want to send you your exam score using RSA. So you choose two primes. Let's say they are 17 and 19. In practice, they're going to be several hundred digits long. And you publish your public key, which is their product n and this number e that I haven't told you how to compute yet. We'll deal with that later. So you publish 323 and 95. Next, in the comfort of your own home, you compute your private key, which is this number d. And only you know how to do that, because you need to know these individual primes to compute it. And we'll learn how to do this in a bit. Then I, the message sender, will use your public encryption function, and I will take your score, plug it in, which is your score raised to the 95th power. So I do that on my computer. Only I know your score. And I reduce it mod 323. And suppose that by doing this, I get the number 307 mod 323. Now this is public knowledge. I can email this to you, Or I can do what I've done previously with classes. I've actually done this, and I've made a Google Doc that everybody can see. And I have posted everybody's encrypted score. So anyone can see anyone else's encrypted score. But that doesn't do any good. Because in order to decrypt this score, you need your primes P and Q. So suppose that I email you 307, your encrypted score. Here's what you do. You use your private key to decrypt this message. You take that score and you plug it into your decryption function, y to the 191 mod 323. So if you do this, you get 307 to the 191 mod 323. And it takes Wolfram Alpha, MATLAB, or whatever your software of choice is, a split second to spit out that this is just 86 mod 323. So that is your midterm score. Let's pause for a moment and think about what in the above process we don't know how to do yet. First of all, we need to find a natural number e that's relatively prime to phi of n. In our example, find an e that's relatively prime to 288. Now that's easy for 288, but it's in general very hard for numbers that are several hundred digits long. Most implementations of RSA actually use the same value of e, which is 65537. Remember, this is part of your public key. There's no need to be secretive about this. You might be asking, well, why does this always work? Well, the short answer is it doesn't, but there's a quick fix if it doesn't. We'll address that soon. The second thing that I glossed over was solving the equation EX equivalent to 1 mod phi of n. Remember, this solution is our private key D. In this example, we had to solve 95x is equivalent to 1 mod 288. Now, this is something that we've already seen earlier in this course. Do you remember how to do this? We need the extended Euclidean algorithm. Finally, the last thing we need to do seems like it's the easiest. It's just plain old multiplication or exponentiation. We need to compute x to the e and y to the d mod n. In our example, we need to compute 86 to the 95 and 307 to the 191 mod n, and n is 323. Now just computing this number, 307 to the 191, is 475 digits long. And I guess nowadays we have computer systems like MATLAB or Wolfram Alpha that can do that easily. But remember, we're using really tiny primes, 17 and 19. So if we didn't have those software packages, it would be a much different story. And in practice, if our primes are several hundred digits long, this number is just enormous. So don't even bother. Fortunately, there is something called fast modular exponentiation, which uses basically a method of repeated squaring to compute this number mod n without actually computing this entire 475-digit number first. Let's begin with seeing how to choose a number e that's relatively prime to phi of n. In our example, n was 323, so phi of n was 288. And as the message recipient, that's you needed to find such an e that's relatively prime to 288. And as we said, for a small n, like this was, this is easy. Just factor 288 and pick a number that has no common prime factors. And you did that. We picked 95. However, in practice, phi of n is way too large to factor. Knowing how to factor n doesn't tell us anything about how to factor phi of n, which is going to be some random composite number that might have many prime factors. However, we don't need to do all that work and factor it. All we need to do is take any prime that does not divide phi of n and use that. The good old method of guessing and checking will yield a prime rather quickly. In a perfect world, a particularly nice choice of E would be the following. Well, it would be prime. It doesn't actually have to be prime, but why not use a prime? It makes it easier to verify that it's relatively prime to 1. And also, ideally, it would be of the form 2 to the n plus 1. Because in binary, we'll see why this is important shortly, a number like this is almost entirely zeros. It has only 2 non-zero digits, namely the first one and the last one. So we're looking for a prime of the form 2 to the n plus 1, and it's a fact from number theory that the only primes of that form are also of the form 2 to the k plus 1. So only very special n's will make this a prime. These things are called Fermat primes. The only known Fermat primes are 3, 5, 17, 257, and 65537. So notice that 3 is 2 to the 0 plus 1. That's 5 is 2 to the 1 plus 1. That's 2 squared plus 1, 4 plus 1. 17 is 2 to the 3 plus 1. I think we did this in a previous lecture. 255 is 2 to the 4 plus 1, and then this one is 2 to the 5 plus 1. And of course, Fermat, back in the 1600s, conjectured that, well, the first 5 are primes, they're all primes. He was wrong. Euler just proved that the next century, and it's still not known whether any other Fermat primes exist. So once again, these are the only known Fermat primes. If there are some, they're many, many hundreds of digits in length at the shortest. Because of the scarcity of Fermat primes, and the fact that using a small choice for E is going to weaken the security, usually the largest known Fermat prime, that is 2 to the 4 plus 1, or 65537, is used in practice. Now, in the very slim chance, what's about a 1 in 6,500 chance that 65537 actually divides this large number, phi of n, then we could go back and pick a different Fermat prime, but it's just easier to go back from the beginning and just pick a new p and q to begin with. Our second problem that I didn't tell you or remind you how to solve was how to find an x so that ex is equivalent to 1 mod phi of n. So recall that we can solve an equation like this using the extended Euclidean algorithm. Now, if you're taking this class, you watch that video and hopefully you remember how this worked. However, I won't assume it. I'll go back and I will review it. In our example, we wanted to solve 95x is equivalent to 1 mod 288. So the first thing we do is create a table, and we're going to have 2 columns, one for 288 and one for 95. And then the first 2 rows are going to be the same. We put a 1 under 288 and a 0 under 95 because 288 is 1 times 288 plus 0 times 95. Next, we always put a 1 under the second number and a 0 under the first number because the second number, 95, is 0 times 288 plus 1 times 95. So this is our initialization part, and now we're ready to really begin. We start by taking 288, this first number, and dividing 95 into it, computing the quotient and the remainder. So 288 is 95 times 3 with a remainder of 3. Now we have 288 in our first row. We have 95 in our second row. So we need to put 3 in our third row. So we're going to solve for 3. If we do that, we get 3 is 288 times 1 minus 3 times 95. So we get 1 times 288 minus 3 times 95. So we take the row for 288, that's 0, 1, and subtract off 3 times the row for 95. So if we take this row 1, 0, and we subtract off 0, 3, we get 1, negative 3. And what that tells us is that 3 is equal to 1 times 288 minus 3 times 95. Well, of course, you knew that from right here, but it'll become less obvious as we continue. Okay, so do you remember the next step in the Euclidean algorithm? So remember that the idea here is that the GCD of 288 and 95 is the same as the GCD of 95 and the remainder when I divide 95 into 288, which is 3. So we have to repeat this process down here. So we have to write 95 is 3 times something plus some remainder. And if we do that, so 95 goes here and 3 goes there, we get that 95 equals 3 times the quotient, 31, with a remainder of 2. So we can solve for 2. That's what we do. We always solve for 2. And we write 2 as some number of 95s minus some number, or plus some number of 3s. So 2 is 1 times 95 minus 31 times 3. So we take the row for 95, which is 0, 1, and we subtract 31 times the row for 3. So here's the row for 95, there's the row for 3. So we take one of these minus 31 of those. So 0 minus 31 is negative 31. And 1 minus 31 times 3, that's 93. I guess 31 times negative 3, so that's 1 plus 93, we get 94. So remember what that means here is that 2 is actually 288 times negative 31 plus 95 times 94. But we don't need that. That's just, it's worth mentioning what these columns actually keep track of. So we can keep going. Now we want to divide 2 into 3 and compute the remainder. So 3 equals 2 times 1 plus 1. So once again, we solve for 1 in terms of some number of 3's and some number of 2's. So we put that 3 and that 2 there. So 1 is 1 times 3 minus 1 times 2. And so these numbers here, 1 and 1, we take the rows corresponding to 3 and 2, and we take 1 of that first row, or 1 of the row for 3, and subtract off 1 times the row for 2. So we take we take this row and subtract off that row. So 1 minus negative 31 is 32. And negative 3 minus 94 is negative 97. Okay, so now we have it. Now we have that 1 is 288 times 32 minus 95 times 97. Or if you prefer, plus 95 times negative 97. So in conclusion, this last number that we got, and again, I didn't write it down, but I guess I could have done one more step to say 2 So this 2 and this 1, 2 is 1 times 1 plus 0. We stop when we get a remainder of 0, and that last number that we stopped at is the GCD. So the GCD of 288 and 95 is 1. If it wasn't 1, we would get some bigger number. And once again, 1 is 288 times 32 plus 95 times negative 97. And from this, we can solve 95x is equivalent to 1 mod 288 by just taking this equation and reducing it mod 288. And notice that this term here that has a 288 in it becomes a 0. And so now we get 1 is equivalent to 95 times, so let's cross that out, 95 times, hey look, there's my x, negative 97 mod 288. So if x is negative 97, we usually like to report this as a number between 0 and 287. We can just add 288 to this, and we get 191. And that's where that number came from. At this point, I need to pause and say something about how feasible this is for numbers that are 200 digits long. And I have some good news. The Euclidean algorithm takes at most 2 times log base 2 of x steps. And by steps, I mean rows. So how big is this for 200-digit numbers? It's actually smaller than you might think. So even for numbers that are 200 digits long, this is only at most 1,329 steps, something that a computer can easily handle. Remember, our last of 3 mathematical challenges was how to actually compute x to the e and y to the d mod n. Even for our small example with 2-digit primes, we encountered the number 307 to the 191, which was y to the d, had 475 digits. Though a computer can easily handle this and reduce it mod 323, that is this huge number, this quickly becomes unfeasible when y and d are no longer 2 or 3 digits long. So when they are 200 digits long. As an example, let's just take 2 large numbers that are in the general ballpark for what we're dealing with RSA in practice. If we take a 185-digit number, we can generate one by just multiplying root 2 by 10 to the 185 and taking the floor. And we can generate another huge number by taking, say, root 3, some irrational number, and multiplying it by 10 to the 180 and taking the floor. So 2 giant numbers. And computing x to the e for those numbers requires over 10 to the 180 multiplications. That's a lot. Especially because our entire universe that we live in is only about 4.4 times 10 to the 17 seconds old. I think I can leave it at that. So our goal is to actually compute this number x to the e mod n in at most 2 log base 2 of e steps. And with the example above, with a number that has 180 digits, this would only require about 1,200 steps. So how do we go from completely infeasible in the life of the universe down to 1,200 steps? We do something that's called fast modular exponentiation. And I'll show this to you with an example. Let's compute 86 to the 95 mod 323. Remember, this was from our earlier example. First, we write the exponent in base 2. Now, I went over how to do this in the previous lecture, so I'm not going to repeat it, but I'll just summarize the answer. It's 95 is equal to 1 times 2 to the 6th plus 0 times 2 to the 5th plus 1 times 2 to the 4th plus 1 times 2 cubed plus 1 times 2 squared plus 1 times 2 to the 1st plus 1 times 2 to the 0. So in binary, we get 1, 0, 1, 1, 1, 1, 1. And here's that number. Next, we can write 86 to the 95 as 86 to the 64 plus 16 plus 8 plus 4 plus 2 plus 1. Notice these numbers are precisely the powers of 2 that correspond to 1s in the binary expansion. So in this case, that's everything except for 2 to the 5th, or 32. Then using the laws of exponents, we can write this as 86 to the 64 times 86 to the 16 times 86 to the 8 times 86 to the 4 times 86 squared times 86 to the 1st. So here's the game plan going forward. So we need to compute this thing, mod 323. I'll summarize it first and then I'll go through it step by step. So 86, mod 323 is just 86. So if we square it, we get 86 squared mod 323, and that's something we can compute really easily. So that's a number that's no bigger than 323. And the square of that number is 86 to the 4th. So we can compute that pretty easy. It's, again, the biggest it can be is 322 to the 4th reduced mod 323. So that's a number we can keep track of. And then 86 to the 8 is just the square of that number. We can compute that, reduce it mod 323, and use that to compute 86 to the 16th, and so forth. And now what we have is each of these numbers, we have 1, 2, 3, 4, 5, 6 numbers that are no bigger than 322 that we can multiply together and reduce mod 323. And that's much easier. See, there we do not have to actually compute this number, which recall, I don't know, has several hundred digits in length. Now what I summarized, there's actually a slightly better way to do that, and I'll show you that in a moment. But what I said is the basic idea. So let's go through that. So notice that 86 squared turns out it's 290 mod 323. And successive powers are 86 to the 4th is the square of 86 squared, which is the square of 290. And it's easy to compute that that is 120 mod 323. Okay, let's keep going. Let's compute 86 to the 8. That is just the square of 86 to the 4th. And we just computed that to be 120. So 120 squared mod 323 is 188. Next, 86 to the 16th is the square of 86 to the 8th. In other words, the square of the previous number, 188, which turns out to be 137 mod 323. You see the pattern? 86 to the 32 is the square of 86 to the 16th, which is the square of the previous number, 137. And that's 35 mod 323. And finally, 86 to the 64 is the square of 86 to the 32, which is the square of the previous answer, 35. And that's 256 mod 323. If you look at how many steps we've taken so far, it's just the log base 2 of this number 95, which is the exponent, in this case, e. Putting this together, 86 to the 95 is this product of a bunch of powers of 86. We don't actually need all of the ones that we just computed, because notice 86 to the 32, that doesn't appear in the binary expansion, or 32 doesn't, so we can omit it, but we need all of the other ones. So we can reduce all of these mod 323 and multiply them together, or we can actually do a little bit better. What we can do is, first, if we write out this product of numbers, 256 times 137 times 188 times 120 times 290 times 86, we could just do them one by one. So we can first multiply these first two digits together and reduce that, mod 323, and we get 69. We can take 69 and multiply that by the next number, 120, reduce that mod 323, we get 205. We take 205 and multiply that by the next number, 188, reduce it mod 323, we get 103. Then 103 times the next number, 137, reduced mod 323 gives us 222. And finally, 222 times the last number, 256, reduced mod 323. That gives us our final answer, which is 307. This is called the method of repeated squaring we did up here, and it's part of the bigger algorithm of fast modular exponentiation. And it requires at most 2 times log base 2 of e steps, because in the worst case scenario, we have exactly log base 2 of e terms, powers of 86 that appear in here, and we have to, well, first of all, we have to compute each one of them here, and then we have to do that many steps again to reduce this mod 323. And notice by doing this one at a time like we did, here we did the first two and then the first three, etc., we never actually needed to compute a number larger than the square of 323. And in this case, it's not bad to actually compute these multiply these 6 numbers together and then reduce it. But when we deal with primes that are several hundred digits in length, it is really a lifesaver to be able to save on time and space in this manner. Finally, I want to conclude by reminding you that I said a couple slides ago why it was a good choice to pick our exponent for our public key e to be 65537. It's because that was 2 to the 2 to the 5 plus 1, or 2 to the 32 plus 1, and in binary, that's almost all zeros. There's only 2 ones. So we still have to compute the successive powers of x, our 86 here, but then when we multiply them together like this, it's much easier. We don't actually have to worry about doing this 2 at a time, because we only have 2 non-zero terms, just the highest power of x and the lowest power of x. Okay, so that's a summary of how RSA works. What I did not do in this lecture is tell you why it worked. Like, why does the d, for example, if you take x to the e, the encrypted message that I send you, why is it the fact that this particular d, mod phi of n, actually gives us what we want? And there's a few other things that I told you how to do, but I didn't really tell you why. Turns out there's a lot of basic number theory behind the scenes, and that's what we're going to do in the next lecture. So stay with us.